What is it saying to you, Mikko?
Screen share. Okay, now.
Mikko, start the screen sharing. There you go. Yippee! Stage is yours, Mikko.
Okay, thank you.
Wait.
Which one is this one? Is my screen. Okay, so based on yesterday's presentation by Miguel, I tried to gather here some practical guidance for the LNA design, but why not? Okay, so short outline, we start from the selection of the transistor size for the LNA design, then go through the Smith chart and using how do we do it, input matching on Smith chart, then continue interstate matching, which we will see later, and then some stability issues and bias network designs on the last slides. And then the practical work is that we design a two-stage cryogenic LNA based on the transistor that was explained by Rodrigo. The problem is that now I'm through the VTT computers, so it's pretty slow, but it seems to work because I dropped the ADS license if I now close the connection. Okay, this slide shows very briefly what are the main things that you need to consider when you select a transistor for your LNA design. On the left hand side in this figure, I have plotted, this is a realistic transistor model that we have been using designing LNAs at JPL at NASA. And in x-axis, you have a unit gate width for a transistor. And on the right hand side, you can see how an actual transistor is sort of formed. So it's a top down figure of a transistor. So on the left hand side, you have a gate. It's this top, it's pretty slow, this pointer here, but the top transistor is a two-finger transistor. So you have two fingers. You can see on the left hand side a gate, and then the two fingers that form the transistor. Then you have in the middle, we have a sort of a combined drain for the transistor, and then we have a source connection on both sides of the fingers. And this is a basic unit cell that we use in an LNA design. So on the left hand side, you can see the schematic figure. So you have a gate, drain, and source is typically grounded. And then that is how you operate then you bias the device and you operate it for an LNA design. And if we go, and I have marked now that there is one finger, it has a certain width. Typically the length is defined by the technology. So if people talk about 35 nanometer technology, the length is fixed. So that's the sort of length of the channel. What we can typically change is the width. So it's the length of the finger or the width, and it's the red circled area. So that one is now plot. If we go back to the left hand side figure, so I have plot x-axis the sort of the width of this one finger, and y-axis is the noise of the finger. It's I have calculated, we can go back to the equations. So TK cascaded minimum noise means that in this calculation, we assume that we put infinite number of these transistor in cascade so that we get infinite gain. And when you plot this kind of a plot, this noise temperature, which is around about 15 Kelvin, is the lowest noise that you can achieve for an LNA when you have designed it with ideal components. So below that one, you cannot ever go. And we can see that using this transistor model, if we scale down the finger width, actually the noise shoots up. So typically, ideally, you would use as short finger as possible because you decrease the resistance of the finger. But in real transistor, once you scale it down very small, the capacitance starts to dominate and other external parasitics, meaning that the scaling does not work anymore and you get higher noise. On the other hand, if you go larger in the width, mainly the resistance, the series resistance of the finger starts to dominate. And again, the minimum noise that you can achieve becomes higher. But there is a sort of optimum area where we can choose the finger width. So here we can choose from 5 to 15 micron, single finger. And another thing is that when you put these fingers in parallel, like in the 2-finger case or 4-finger case, ideally, the noise or gain doesn't change at all. So you can put ideally these fingers as many as possible in parallel, like in the 4-finger case, and you still get this lowest noise possible for this technology. So what you can do now is, one thing that you need to think about is that you need a certain size for the transistor, and that you can see on the Smith chart in the middle. And we will come to the matching of the amplifier later, but you can see that based on the finger numbers, you can change the desirable input impedance for the transistor. So from, if the 50 ohm is the middle, so we need to match it to the point on the Smith chart. So there is also a circle which is it 1.15 times worse than the optimum 15 Kelvin which you could achieve. So now, so you first choose the 1-finger optimum. Here it's 5 to 15 micron. So I have chosen 15 micron because I want to move on a Smith chart to a certain point. And then I have, actually in a real amplifier, I chose 4-finger transistor because I know that on that point it's easy to match to get a wideband response. So this is how you would start selecting your transistor size for your design. Of course, another thing is that you need to first play with the biasing. So if you have too low current for the transistor, the noise and gain are poor. So you want to have a certain bias. You can play that one also with the sophisticated transistor models. But that's fairly easy game. But the finger, this kind of a unit gate width thinking is, in my opinion, the best way to start the LNA design. And then, then the next step would be that we would need to design that input matching network for the transistor that was selected in the previous slide. So yesterday Miguel showed the Smith chart. I find it very useful in the LNA design. Some people do it without Smith chart, especially at lower frequencies. You can sort of calculate the values that you want, the inductances and stuff like inductances that you need to, but there are certain rules that you can then, we will hopefully understand it in when we do the practical design, that for example, if you put a short-circuited shunt stop on the left-hand side bottom figure, if you decrease the inductance, this is a short-circuited shunt stop towards ground, you can move on a Smith chart through the admittance plane. So you can see that you can go that direction. Increasing shunt C would be an open shunt stop, and you could move on the other way around. And then there is increase in Sirius and Sirius C, so you can play with those one. And in radio engineering, you might remember that if you are having a serious transmission line, you can circle the center of the Smith chart. It's not shown here, but you can easily test it in a circuit simulator. Then on the right-hand side, there is a basic figure of Q circles drawn on the Smith chart. The lower the Q, the wider band matching network you design. So if you start from the middle and you go on the edge of the Smith chart while you are matching, that will result in very narrow band design. So this basically shows that you want to stay much in the middle as possible to get a wide band response for your matching network. Whoa. Okay, it's going here a bit faster. Sorry. Okay. This is one few figures of one of our papers. So on the top right-hand corner, we show that this is actually a CMOS transistor where we again select sort of a appropriate size for the transistors by putting fingers in parallel. So in the A figure, we have 9 micron transistor. So I guess it's 9 transistors in parallel. Then in a B18 and in C27 and D36 micron wide transistors. So fingers in parallel. So you can see that there's a different frequencies shown for each of the designs. So we can see that we again can move on a Smith chart to a point that we can match a wideband match. And on the left hand side, there's a realized input matching networks used in our design. So if you start from the left from the RF input, that's our 50 ohm impedance. So that's the middle of the Smith chart. If we want to, if everything is referenced to 50 ohm, as typically is. We have a pad and a series capacitor for the bias, so that the bias doesn't leak to the antenna. So on the right hand side, you can see that actually the pad is capacitive towards ground, so we will move on a Smith chart to point ZA. That's part of our matching now. That is what we cannot much affect because the pad is there when we need to wire bond it to a circuit. Then we have added a series transmission line. As I said, the series transmission line moves around with the putting it longer, you can move around the center of the Smith chart. So you can see that we move on point ZB. Then we have now the short circuit shunt stop, which moves on. You can plot this Smith chart is on impedance plane, but you can plot it as was in the previous figure on admittance plane. So it's like a reversed Smith chart. So there you move on the admittance circles to point ZC2. And now, if we would select a transistor, a really small one, we would need to match it to point Z. Is that U, the one on the right hand there? So we can see that with the series line, we could move there, but as we remember that there is also plot that Q circles. So we will go quite close to the edge of the Smith chart. So that would lead to narrow band design. Okay, so since we were clever enough, on right hand side we chose a transistor which is much larger. I think it's that 36 micron one. So there it's easier to go from a little longer short circuited shunt stub and then move with the serious line to point ZX, and we don't cross that Q circle. So this now leads to a wideband design. If I remember, Q1 circle is like, I think Kristi calculated, I would need to check it in one of the papers, but it's like you can design a Ka band amplifier from 26 to 40 gigahertz. So in percentage, that would be, I don't know how much. Yeah, something like that. So that would be Q1 circle, yeah. Okay, did we jump something? Okay, input matching is there. So we will start soon the design on that part. So then how it would continue, we would then add the first transistor to our design. We would design for the second transistor similarly on a Smith chart to optimum, maybe optimum noise. Here we can, if the first transistor has a lot of gain, we can also design the second transistor for gain matching. But here I have marked it that it's the optimum noise match. And then depending how much gain you want from your amplifier, you add stages and continue this as much gain as you want in principle. And then finally, we would add the output matching back to 50. Then we can go this one too later once we have designed our amplifier. So then important part is the bias network for the design. So how you actually implement an RF short-circuited shunt stub where you can then bias your transistors, that you add a capacitor. I have shown that that's in sort of RF short, so I have added capacitor, and if the capacitor is large enough, that will be shorting the RF to ground. And if we have a piece of a transmission line, that's our short-circuited shunt stub, which we can both use for matching. And since that point is an RF short, after that we can add like a resistor to stabilize the circuit at lower frequencies. So our sort of RF signal doesn't go after that capacitor when it's large enough. On the other hand, it should be small enough so that the lower frequencies that usually generate stability problems, that means that the circuit starts oscillate. It has to be small enough so that the resistors that will stabilize the circuit are seen by the lower frequencies. So there is one game that we need to play when we sort of design the amplifier. And then soon we go to the practice work. So this was already uploaded to the AWR or to Google Drive, and we need to put it in practice to AWR. So we will use this transistor model to design our circuit. Just few words of some ugly looking equations first is that important is to understand for microwave engineer is the, Miguel was yesterday saying, the noise measure for an amplifier or for a transistor. So it means the one that I plotted in the first figure is that this is the measure which takes into account the gain of the transistor when you try to figure out how low or how good low noise amplifier you can design. And this should be taken into account when the available gain for the transistor becomes low. Let's say well below 10 dB, or actually I don't have a good number for it. We can look at it in the simulation soon. So at low frequencies, usually this doesn't need to be thought about because we have a lot of gain from the transistor. So it means that the first stage is already dominating the noise performance. But if we have really low gain, like 5 dB, all of the stages starts to affect to the noise figure of the receiver. There was that freeze formula which we went through. So if we have several amplifiers with low gain, all of the amplifiers starts to affect to the noise figure of the receiver. So this is important to at least remember at this point, since we are microwave engineers. And one important thing is that once you have plotted that, maybe we should go back to the, or does it go too slowly? So I'm talking about coming soon. So I'm talking about this, where we selected the appropriate number of fingers for the transistor. So this TCAS-min, that is now the minimum noise that you can achieve when you put infinite numbers of these transistors, amplifiers, or amplifiers in cascade. And this is not, this doesn't change if you embed your transistor with any kind of a lossless matching network, feedback, whatever you add around it. That doesn't affect this number. It will affect the number that usually is used at lower frequencies, which is the sort of minimum noise figure of the transistor. So again, yeah, this will go down if you cool it, yes. So that was a cooled transistor. Actually used, that model is used to design the LNAs that were in that Green Bank observatory. So that is the model, not this one, the one that was in the first slide. Yes, so that is from that transistor used to design the amplifier. What does it affect? Or
what determines the number of fingers in other metrics?
It only affects the output power. And also it assumes that when you have doubling the number of fingers, you also double the current, right? It's like a cell that you copy. So you burn twice the power too, because it's a fixed like cell. And what we do is that we move on a Smith chart to correct place. If we are, then we are in trouble if the system is requiring like super low power consumption and wide bandwidth, because then we cannot move on the Smith chart, right? So then you are in a bit in a trouble how you're gonna do it if you are tied in a power consumption, because putting fingers in parallel means that we burn more power all the time to move on Smith chart. Okay, so we now know that this TCAS-min is invariant to any lossless network that embeds the device, so it's around the device. But it also means, which is a good thing, that we can add a low loss source feedback. This is the degeneration source feedback that Mikko was talking about yesterday. And that's a very useful thing in LNA design. First of all, it can be used to bring the optimum noise match and the input matching closer together. So with that feedback, we can design our optimum noise match condition, but we can also have a good matching at the input. So if we wouldn't use this one, it could be so that we have a good noise performance, but the matching is poor. But with this one, we can do both at the same time. And second important thing is that it affects the stability of the transistor, which we will soon see. So we can stabilize it too. And it doesn't affect our noise performance of the total LNA. Okay, so the equations are pretty ugly for the noise measure match, which I've been talking about. But remember, at lower frequencies, when the gain is high enough, we don't necessarily need to use these equations. And we will not start using it in this practice. But you should remember, if you start to design later on an amplifier, not jumping around. Okay, no. And now I did in ADS a simulation for the transistor that you have. I have here simulated. The red one is the one that is the TCAS min that I've been now talking about a lot. The blue one is minimum noise figure, which you usually get when you get your transistor. If you buy a transistor, for example, or they give you the data, as Miguel was discussing. And that is minimum noise figure or noise temperature. That is given. But you need to use the equations in the previous slide to calculate the infinite number. If you cascade infinite number of these transistor and make a matching network with ideal components, that is the one that you end up with the red curve. You can see when the gain goes low, I have also plotted the available gain in purple, or is it pink? When I have matched the input to the optimum noise of the transistor, and the output is conjugately matched. So you can see that when the gain goes low, below 10 dB or 10 dB, TCAS min starts to go higher, but NT min, you would make a wrong decision of the performance of your LNA based on NT min. So in real life at 100 gigahertz, you will get 30 Kelvin noise temperature of your LNA, not 25 Kelvin. But today and tomorrow, we will focus on the design of 26 to 40 gigahertz LNA. And we can see that at those frequencies, they don't differ that much. So we can use the traditional equations for designing the LNA. But again, it's good to remember the importance of this TCAS min here. And on the right-hand side, actually, you can see it on Smith chart. So that would be the optimum. The red one is the optimum TCAS min match, that where you should match it to get the lowest noise possible for your LNA. But we can see that the optimum, this is in the textbooks, the optimum noise figure match is the black one. So they are on top of each other. So we can now use the traditional equations for designing our LNA.
What is the impedance that will give you optimum?
It's the red one.
Yeah, that's what one is in the cascaded case, and the other one is the intrinsic.
The other one is the only one transistor that you would match.
So this is for input in particular?
Input. This is the input. This is the impedance that the transistor wants to see at the gate. Yes.
And so at the beginning, when you show us the transistors with different figures,
Mm-hmm.
and you showed a point with a circle on the Smith Smith chart is exactly that.
Exactly. We can go back, but it's pretty slow.
Yeah,
Here. Exactly. So there we are. So there is a tiny point in the middle, and then we have plotted this circle, which is 1.5 times, 1.15 times the minimum. We can also see that we don't necessarily need to hit exactly the center because it's 1.15 times. So it's like a trade-off of the bandwidth and the performance. So here we are not hitting the minimum. We are hitting inside the 1.15 times for this design, because we want to stay in the middle of the Smith chart. And you can see ZXU in the schematic on the left-hand side, which want to show that impedance to the gate of the transistor. So fairly straightforward. Okay, did I something? Okay, before we go to the design task. So then there's another thing with the stability. So this is the previous slide was also simulated without the source feedback, and I mentioned that that can affect the stability of the transistor. So on the right hand side we can see that the mu factor and stability factor on the right hand side were the stability measures for the transistor, which we learned yesterday. So you can get this one from the simulator easily without going through the equation. And they are all below 1 for the whole frequency range. So it means that the transistor is potentially stable, unstable all frequencies. And on the right hand side, you actually see it when we okay, let's go to the next slide. It's not easily seen here. No, not that one. So now I added a feedback to the source, a 150 micron long feedback. And I can see that at 40 gigahertz or below, I have now improved the stability so that actually at that frequency, the transistor is now unconditionally stable for all passive loads shown at the input and output. So this is one thing that you need to consider, that it's better to start with a very stable case rather than trying to get everything out from the transistor. But at the same time, we can see that the gain dropped down quite heavily because we introduced feedback. But remember, the TCAS min shouldn't be changing at all. It will change a bit because we have a little bit loss in the feedback. But if we go to the previous slides, we should still be able to design a below 10 Kelvin amplifier at 40 gigahertz. Okay, it's not changing. So the TCAS min didn't change here. So now, on another vision on a Smith chart, Miguel nicely presented the stability circles and the circles of optimum noise match and gain yesterday. So here we can actually see that on the left hand side, with 80 micron source feedback at 40 gigahertz, there is a tiny part of the Smith chart that is on unstable region. And the purple one, pink ones are the gain circles. So maximum gain, and then there's a gain step of 0.3 dB. So if you match there, you would get also almost the maximum gain out of the transistor. And then there's optimum noise match and the S-opt, which is the traditional measure. And on the right hand side with the 150 micron source feedback, the whole Smith chart is stable. So the blue circle is outside of the Smith chart. And I think we should now start by matching the input of the transistor which you have with this 150 micron source feedback, so that we have a stable transistor. So maybe can you, Miguel, plot? Now we would need to know how to use AWR. So can you plot the S-opt on Smith chart? The one that I just had there, and you have the 150 micron feedback there, right? Yeah. Okay. So we are now on that one. Ah, okay.
But it's an introduction that it is inside there is a model that is a transistor that Rodrigo is. And those different parameters. I hope you can hear me. Okay. So simply saying that this is the file that you have. So if you open it on AWR, you have this main schematic named as LNA that you can open it. And inside of it, there is the model of the transistor that Rodrigo, in fact, developed this during this night. So he didn't sleep at all, but managed to create it. And it's exactly the model that we can find at the paper. And it has all the different parameters that are indicated in there. So what we have here is a two-port finally network, and we can plot in the different section of the graphs the input and output, and for example things such as the S11 and S22 parameters. But in this particular case, having the this transmission line, that is a microstrip with this kind of substrate that we are working with. And when Mikko indicates that he has transmission line of 150 microns, is in fact 0.50 millimeters. So this is exactly the same that he has on ADS. Okay, this is a good question indeed. I don't know if anyone here, Rodrigo, but Mikko provide the parameters based on the simulation of the silicon.
No. This is a typical gallium arsenide.
Gallium arsenide. Okay. Okay. I didn't know that, so it's a good question even for me. I think the people cannot hear you at all, but so in order to put it on the schematic, we did it similarly as Rodrigo did on the introductory card. And in order to provide the transmission line, what we did was using the microstrip transmission line. So you know now exactly how to manage that. And okay, that is.
Can you now plot the? Can you, Miguel, now plot the S-opt on a Smith chart? And remember, it's noise. Should be DS opt. Yep.
Probably this is what the one. I don't know, 2-1 or 1. But we are matching for noise at the.
Yeah, I would guess it's 1-1. Yeah.
One particular
40 gigahertz.
doesn't work for me either. Okay. So in this case, I need to select here.
Okay. So I think you are close where I was, right? It looks like. I think it's there. I hope. Okay. So now we would need an input matching network to move close to that point. We will do it at single frequency, 40 gigahertz. And usually how I do it, I start from the highest frequency. Maybe I will even push it to 45 gigahertz because usually it starts to roll off if you design it exactly to 40 gigahertz. And then after I have finished the initial design, I sort of start tuning by hand the network. And let's see if this is a correct way of doing it. So now I would now design an input matching network to get close to that point.
They understood that you were questioning. Is they are not hearing you. So, is what is in fact the blue one? Exactly. It will depend on the input impedance. MIkko is plotting the thing, but the thing is that this is the optimum impedance, meaning that it will be the best for noise. But we are not there. If you plot the impedance of the yeah, it will depend on the Smith chart where you are. This is the S parameters. It's not the impedance itself, but you can also plot the. And as MIkko said, we need to do this kind of turning into the Smith chart, doing those jumps in order to get this optimum value. Rodrigo, I don't know if you can point the camera to make the people see what MIkko is doing.
The idea is that is the optimum somewhere.
Yeah.
So we plotted this optimum noise match for the transistor. that it wants to see. So we start from 50 ohm. We are here in the middle of the Smith chart. So now we should make a matching network that we get to this point. And that's the one that sort of we present to the transistor. So then it's noise matched. So somehow we should get here, and we should get as sort of, let's draw one guessing cue here, that we stay inside close of the Smith chart, not like going here and then here. That would be a really narrow band. If we stay close to the center of the Smith chart, that leads to a wide band. And okay, one thing that we didn't mention is that since this is we are sort of trying to copy what Pospiet-Salsky was doing in the paper for the 26 to 40 gigahertz LNA. So luckily he chose the transistor size so nicely that we most probably, if we go as close as Smith chart to that point, we get a wide band amplifier. So he did it for us. So we start from a good transistor selection. Okay, want to try? So,
Corto l'audio.
Yes, to do.
What time is it? Could leave it on. If it's not leaking water, I guess it's no more leaking water. It's ready. Let it run. We're not there, so.
It explodes, yeah.
It's ready for tomorrow. Okay. So now we would need to add some kind of a matching network to get there. I propose to add a short circuited shunt stub now. Before. Okay. So now, since this is AWR, we would need to sort of forget the transistor for a while and sort of make a 50 ohm input. Maybe we can do it here.
I have a question. Are your slides on the drive?
Not yet.
There are the circles that you can do shunt.
Yeah. Not that large, I can email it maybe to you.
Vamos a subir su diapo porque mostró estos círculos en la carta Smith. Impedancia que lleva viaje por la carta Smith en cierta dirección. Y lo que nosotros necesitamos hacer es efectivamente hacer un camino. Entonces, si uno se apoya en estos círculos preestablecidos donde la posición de la impedancia se mueve de cierta forma en la carta Smith, te hace más fácil elegir qué es lo que hay que agregar para poder llegar al punto que a ti te interesa. No, porque en la carta Smith tú tienes un óptimo que ya está ubicado en la carta Smith. Entonces, claro, pero tú partes desde afuera del circuito con un puerto que es un puerto de 50 ohms. Está en el centro de la carta Smith. En la entrada. Entonces, ¿cómo llegáis desde la entrada hasta el transistor? ¿Cierto? Que ya tiene un óptimo. Entonces tienes que juntar el punto de 50 ohms con el óptimo. Entonces, ¿qué camino tomas para llegar allá? Es lo que te ayuda a decidir ese tipo de
te digo porque que tengo aquí, la verdad, un tipo de etapa de impedancia te va a generar cierto camino. Y puede partir para cualquier parte en realidad. Pero tú lo decides. El factor de calidad. Entonces, si tú quieres mayor ancho de banda para tu diseño, te tienes que quedar muy cerquita de la línea horizontal de la carta Smith. Claro, hay veces que el óptimo de impedancia ya está en la orilla y no te queda otra que para llegar allá ya sabes que hay que quedar con un ancho de banda que es súper pequeño, pero no te queda otra porque allá está el óptimo. Entonces, si tú quieres aumentar el ancho de banda con un óptimo que es malo, entonces ya sabes que vaya a ir a un círculo de ruido, porque esta posición en la carta Smith que nosotros conversábamos es solo el óptimo. Entonces, si uno quiere echar a perder un poquito el ruido, toma un círculo alrededor del punto óptimo. ¿Ya? Entonces tienes ahora todo ese círculo que te va a dar un poquito peor ruido, no es el óptimo, pero te va a permitir acercarte hacia el centro y agrandar un poco el ancho de banda. Sí.
Y otra cosa es, comentó así a la rápida, el tema de que se puede mover ese óptimo haciendo la degeneración, que es poniendo, por ejemplo, ese feedback, que básicamente es lo que lo tenemos de hecho en el diseño, pero no es más en este caso que una impedancia, que es una inductancia. Con eso consiguió mover a un sitio que sea un poco más cercano hacia nosotros y así nos facilita la vida para encontrarlo. Lo hizo mediante esa técnica. So, let's translate to English language.
Yeah, so I propose to add a short-circuited shunt stop. I guess you can just copy that one and that's your short there. Let's keep it. Okay. No, short-circuited like this one. Short here and it goes there, and we.
You mean like?
No.
Going from which side?
That's good. Leave it there.
Okay.
Then add a wire there and a ground there.
Okay.
Short-circuited shunt stop. Okay. You need a ground there. You can maybe copy that. No, we would need now to forget the transistor for a while. Problem is that you will now maybe overrun your previous simulation. So
why if I generate a sequence command?
Yes, exactly. There's now two options. I can try in ADS or we do it here. I think it's better to do it here. Let's see how. Yep. And it could be a fairly long one. Let's say, can you tune it? Okay. So now if you can take the same Smith chart where we had the optimum, where we have the optimum noise point. Okay. It will simulate everything all the time. Okay. Okay, that could work. That could work. Yeah. And yeah. And S22. To actually we don't have any line between. I'm not sure if this will work. So you need to add a piece of a line to the input first, because they are now short circuited. Just tell like a 50 micron line there. No, only at the input. Okay. That doesn't need to be tunable. It's just a line. Substrate is missing. Okay. Whoa. Why did it start from there? It should start. Is it the frequency sweep or sweep of that length of the line? Okay, that makes sense. That makes sense. So I would like to see it at 40 gigahertz. Okay. Can you now tune it on the fly? The length of the short circuit shunt. Okay. This is cool. Yeah. So remember, induct. It would be good to see the slides at the same time. But if you make it a bit longer, it's a shunt inductor. So whoa, yeah. Finally, it will go to the middle of the Smith chart right over. It should be like Okay. Okay, there we are. So remember, we had a short piece of a serious line that moved a bit from the center. But now you could move with this was a short circuited shunt stop, and did you upload the slides to the? So there was that figure. MMS elements. That one.
Sorry about that.
Maybe you can scroll down that. Okay, there it was. So what you added was shunt inductor to ground. So you can see decrease in shunt. That was the short circuited shunt stop. So by decreasing the length there. So if it's 1 micron long, you have shorted, so it goes to the short, right? So with this one, you can now, as you showed, you can tune it to a correct place on a Smith chart.
Let's see. So can you show
Whoa.
oh, so you're increasing the length. If you increase it, you go to the other direction.
And decreasing, yeah.
And increasing is the way. Yeah.
Maybe there.
Question, it won't matter that this
You can make that a bit maybe shorter, maybe. Try to take it out. Yeah, I'm not sure.
let's see what happens.
It should work.
You're still there.
Now you start from the middle of the. There's some error there. Might be that you shorted the input and output port. So we need a tiny piece of a line there. It doesn't like a 20 micron or whatever. We need something there anyway, but yeah, like a pad, right? Yeah. 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 Okay, so go somewhere closer. Yeah, maybe there. Good.
So the running is 353.
Sounds quite short. Let me see. I went to this practice once. Okay. Sounds good. I have a 100 micron line at the input, which is 100 micron wide, like modeling the pad. So yeah. And then I have a 350 micron long short circuit. Where did you end up? Okay. Makes sense. It works. Okay. So now if you go back, you are on the Smith chart. Good. So you can see that if you remember that a series line goes around the Smith chart, right? It's not shown there, but that's the basics of the series line. So you can circle the Smith chart. So now if you add a piece of a series line, you are really close to the optimum, right? Yeah, and that's it. Yeah. So you can make maybe that one tunable too. So. You got it already. So, but you can show it, okay, if it's long, if it's short. Okay, you can show that you can go around Smith chart if it's very long, right? Oh, now it's too long. Yeah. Put a series transmission and you can go around the Smith chart. Okay. Don't go just a little bit, maybe that one, yeah. Okay, there you go. But one thing in my slides was that if you plot the noise circles, so the versioning of the noise, so actually you don't need to hit exactly. You can be a bit below to make it more wideband. We don't get that much hit on the noise figure, but you can stay there. Yeah. So that's the input matching. So now you would take this input matching network, put it back to the LNA. Or wait a second. Yeah, let's do it that way. Just thinking, how does the AWR work? But then we will lose again the point on the Smith chart. So we will need to bring the transistor here, right?
There is another way. That is
Okay.
it's not working. This is the one that we are working with. But in this case, we should not plot the optimal value, but we should
Where are we now? I didn't follow. Are we at the output of the LNA?
the output.
Okay, LNA working is now having the matching network, and you will add the transistor there now. Now the first transistor is matched, right? So we add the transistor to the input matching network.
See the second formula.
Exactly. Now we need to match for the second transistor. Okay. This is output of the transistor. So we are looking. You can show it maybe there, yeah, where we are looking at now. The schematic. So yeah, we are looking towards that direction, yes. And now again, you should add a matching network to get to the optimum or close to it.
Space, we do the same. We use an output impedance.
Yeah. I would suggest to have a piece of a series line. And if you go for a while for my slides, there's one thing that we need to consider too. So if you go one of the schematics downwards, one more here. So remember that the short-circuited shunt stub is also used for biasing. So we need to both bias the output of the first transistor, the drain, and the input of the second transistor, which is the gate. So I suggest you to have two short-circuited shunt stubs there at some point, yeah. And then we would have a capacitor there, enough large. Let's say 2 picofarads at these frequencies. Or yes. Yeah, you can maybe freeze down the input. I think you need to go to the LNA working, right?
But we are doing the same.
You need to start from the L last transistor output. There, you are now there. So now you start adding stuff in the LNA working. You will move there, right? I like this one. Go to the LNA working. Yeah, so now if you add here, yeah, at the output, a serious line. Yeah. No, we don't need it at this point anymore. Actually, everything can be done here, yes. Yep. Yeah, you need the bias one that you can use for matching to. Let's do it first that you connect to that point with the S22. Otherwise, it's gonna be a mess. You need to do it step by step. Yep, only the serious line. Only the serious line at the output. So you can. That shouldn't do anything, yeah. Just wire it now. Okay. Tune it. Maybe this interstage matching is the most tricky one because you have now so many options as we will see on the Smith chart, right? Okay, so if you tune it a little. Ah, okay. Remember, you need to have you must have the short circuit shunt stop somewhere. So don't go too far away. Maybe 250 or 200. How much is it now? It's 100. No. Where we can see it? Nowhere. Okay.
We add the following
Yeah, and now you add the short circuit shunt step. Yeah.
first one.
First one. So you want to see where you move. So you can just activate. Yeah, you are there now. Yep. Okay. Maybe it could be a bit longer. Which one is that one? Cannot be. Yeah, now it makes sense. So don't go too middle. Maybe we need to add. Yeah. So 400 or something like that. Maybe that could be a bit longer, the serious line. You are now on the wrong side of the Smith chart for some reason. How it went? That's the no. Keep that one as it was. Yeah, but the serious line, I think you changed the length, or did you? If you make it a little longer, I think we will. Yeah, like 200 or something. That's okay. Let's keep it there. It looks good. Okay. Yeah. Okay. Now you add all of the serious stuff there. Yeah, all of them. That's one piece of a series line with the capacitor. How large is the capacitor? Is it 2 picofarads? You can put it a bit larger. 2 picofarads, 2000 femtofarads. The whole series network is one series line for us now. Or either one. Remember, they are one series line, so you can do either one or both. Doesn't matter. They are in series. It's one long line. Yes, so you need some length. So this is now ideal capacitor, but in a MIM capacitor, actually, you can model a MIM capacitor like this, that in the middle you have the ideal capacitor. You have 2 transmission lines like this, right? Nobody else saw it. Okay.
So everyone is seeing it. And then we can put a very short line.
Then you can tune that one.
This one is 0.02.
So output is not connected, I bet. It's an open circuit. Yeah, we don't want to go away from the point. Don't go too long. Remember, you need to add one short circuit shunt step. Maybe a little bit. Yep. Well, that's good. Yeah, 0.1. That's a good guess. Yep. Yes, again you are moving on admittance plane. Can you get an admittance plane on this Smith chart? Can you right click it? No. Options. Ah, there you have admittance grid. Add the admittance grid. Oh, remove the impedance grid for a while. Okay, so now if you again tune the short circuit shunt stop, you can see that you are moving on the admittance circle, like in the PowerPoint slide. So theory is working here in practice. So now this is your last option to move on admittance plane. Then you have one series line, right? So you go higher. I mean higher on Smith chart. Yeah. Remember, you have one series line left, so you will go around it. So you need to go maybe a bit higher. Yeah.
Yeah, I don't see a
No, actually, you will go. Remember, series line goes you around the Smith chart. It doesn't follow the admittance or because series line has both capacitance and inductor, capacitor inductor. So it's following. It's actually following the figures that we have, but you have a really short bit of a series inductance and then a capacitance towards ground. So it will follow but it will make a circle at the end. Okay, good, looks good. Then we add the series line. Looks good. Yeah, you are there. That's good. That's good. It's enough close. Remember, you make it always narrow band if you go there. Remember the Q circles. So you want to maybe stay below. So what we could do is plot the S opt circles. That if you go far away, which I have it in the slide set. Yeah. It's good there for a while. We can tune it later. We need the output matching and we want to see how it looks. And now we add the transistor again. The second, this is for the second transistor, right? Yes, you copied the whole thing there. Are you bored? Are you already bored? Yeah, so I guess we have 2 hours to. Almost a 2-stage amplifier, but there's a lot of things to do after this. But we could add the output matching and see how it looks and continue tomorrow. It won't look good because we don't have any stabilization RC networks there, right? Yeah, yeah. Output matching network. So same thing, you continue. Now you want to get to the middle of the Smith chart. Yep, yep. I don't suggest. You want to see what happens on the Smith chart. Smith chart is your friend, although it's looking scary.
This is a good sentence.
Yeah. I mean, this is how you use it. There's not much. Yep. Mhm. You want to get, it's the output matching. You want to match it to 50 ohms, so to the middle of the Smith chart. It's possible, yes, but remember where the short circuited shunt stop is moved. Now it moves up, decreasing shunt L. Okay, one thing is that when the short circuited shunt stop is quarter wavelength, it's an open. And from that point, you start to decrease the length. So then you move up. So if you go back to the Smith chart, I have a suggestion for make it a little bit shorter. More, still more. Go. More.
So you go to the real part or
Go. There. If you now add short circuited shunt stop, you will move up. Yep. You could have done it with the open shunt stop from the top to go down. Yeah, you could have done it so, but there's no reason because we can use this bias stuff, which we anyway need, right? You are there. Well, it seems that I have 190. So we are on the same page here. Yeah, some kind of a, I would put there a white line that is like a pad where we can wire bond, right? 100 times 100. Yeah, wide, because it needs to be a big one if you want to wire bond it. Yeah, we can add it. There was a piece of a line, but yep. It's a really wide one, but it's a pad. You need to get to the chip, right? So if you go to the guys who wire bond, if you talk about pads that are smaller and smaller than 100 times 100, they start to be angry. You can go up to 60 times 60, but then you need to be good friends with them. Yeah. Yeah. But no, it has to be 100 micron long. It moved a little bit. It's like a shunt capacitor actually there. But it's close. Don't worry, it's a wideband design. We will need to anyway tune it a bit. That's 1 point. Yeah, so now it works exactly at 40 gigahertz, I guess. So if you now do a frequency sweep for your LNA, let's see how it looks like. Might not look very good yet. So can we plot an on a dp scale, rectangular, S21, S11, S22, and noise? It's scaling. We want to have TE. Or is it TN? What is TE? Yeah, TE. Yeah. Or input, yeah. Yeah, exactly. Then you need to rescale it. -20 to 20, -20 to 20 maybe. -20 to 0. Okay. 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 No, that's 20 Kelvin, but it's 10 Kelvin too high. I don't get it now. We were aiming for, it was 10 Kelvin, right? TCAS min, but once you have a lot of gain, TCAS min will be the same. So we have more than 10 dB gain, so we can look at TE. We could plot it there, but it should be fairly close. But didn't we start? Where are the slides? Something is now wrong. I think we should be at 10 Kelvin. So something is wrong in our design.
So we are seeing it in the thread.
We should be at 10, but we would need to together, maybe the class is ending. Is all the components now 20 Kelvin ones? Where did you define it?
Go to the options.
Okay. No, we cannot cheat physics. The cryocooler goes only to 20 Kelvin. Measurement noise floor temperature. I don't know what is that one.
Maybe it's the minimum that you get.
Okay, but let's look at the shape of the. We need to figure out what is with the noise temperature, but the shape doesn't look yet really good. But at 40 gigahertz, we are about there. That if you go back to my slides, not now, but there was a gain associated, which was maybe around 7 dB when we added the feedback to stabilize it. Yeah, it's around 7 dB. So we should obtain at 40 gigahertz below 15. Okay, we are there, right? So we designed it for a single point, right? So it doesn't look good yet. So tomorrow we need to start adding those RC components and other stuff to get the gain down from that peak, which seems to be actually close to our band, which is not good, but I think we hopefully will manage it. And most probably, if you plot now the stability factor, it's unstable or potentially unstable on that peak area. So basically at this point, the sort of black magic of LNA design starts. You need to make it stable. It's 2 K factor 2.1 maybe. Yeah. Yeah. Let's see what it plots. So there it goes. Maybe the scaling is quite bad. So it's, if you can zoom in, I think it goes there somewhere below, maybe 1. Yeah, it could be in a different graph.
Let's create another one.
And then scale the y-axis 0 to 10, for example. Okay. One. Okay, yeah, it looks good. Yeah, so it's unstable at 20 gigahertz, where we have the peak. So that is what we need to fix tomorrow. So that's part one, noise matching of the LNA at single frequency. Using Smith chart, not scary.
No one can see that the audio is broken.
Yeah. It is. Don't be scared.
We need to put it, you know.
Yeah.
She's saying a good point that previously we need to use the Smith chart with a compass. We need taking the length. And so on.
Ah, you mean by hand?
This is
Yeah,
easier.
by hand. Yeah,
Yeah. So,
but you need to do it to understand it. Now you can use it like this more easily.
any words that you would like to say as
I guess that's a good wording that Smith chart is your friend. Don't be scared.
spooky? Spooky.
Yeah.